Hello, this is Mrs. Lim, your physics teacher, and in this video, I'm going to go through about what are the processes that involves a change of state. Okay, so let's do a very quick recap. We learned that in your kinetic particle theory that every particle, every matter has particles inside them, and these particles are in continuous random motion, and therefore the particles have kinetic energy because of their random motion. And they also have another energy known as the potential energy because of the forces of attraction between them. So we know that the internal energy of any substance is made out of the total kinetic energy due to the motion, as well as the total potential energy because of the forces of attraction between the particles. So internal energy is actually equals to Ke plus Pe. Then we are going to zoom into what happens during the change of state, what happens during the kinetic, what happens to the kinetic and potential energy as heat is being added to a substance or heat is being removed to a substance. Okay, so you'll be able to go through these changes of state like melting, solidification, boiling, condensation as a process of energy transfer without a change in temperature, and explain the difference between boiling and evaporation. Okay, so these are the cycle of a change of state. So you have from ice, it will melt to become water. So melting is the process whereby ice, solid, changes state into liquid state. Okay, when you add heat to it, okay, so it's a red color arrow. Heat energy is being absorbed in order to change from solid state to liquid state without change in temperature. Similarly, from liquid state to steam, okay, from liquid to gaseous state is boiling without a change in temperature. And then opposite way, when you cool down, vapor will condense into water. So it's condensation from gaseous state to liquid state. And from liquid state to solid state is solidification or freezing. Okay. Okay, so we know that you need to know certain things that the temperature at which all these changes in state occurs are called the melting point, freezing point, boiling point, and condensation point. Okay, and during this particular temperature at which it melts, freeze, boil, or condense, the temperature remains constant. The temperature doesn't change. So for example, water, it has a fixed melting point. So your ice have a fixed melting point of 0. It also have water has also a fixed freezing point of 0. The melting point and freezing point of the same substance is the same. If I melt at 0 degrees, I will also freeze at 0 degrees. Similarly, if I boil at 100 degrees, I will also condense at 100 degrees. It's just a reverse of the process, but the temperature remains constant during all this change of state. Okay, and so with the fact that the temperature remains constant, we should be able to get a temperature time graph that looks something like this. Okay, so initially, I have a solid state which looks like this. Okay, all the particles are very closely packed in an orderly arrangement at time t equals to 0. I were to add heat to it, the temperature is increasing. So it's a heating curve. I'm adding heat to it. Okay, so as I add heat to it, okay, the first step is the particles in the solid will start to gain kinetic energy, will start to vibrate faster. As it vibrates faster and faster and faster, okay, what is happening is the kinetic energy of the particles increases. The temperature, which is also links to the kinetic energy, will increase. So during this section, you will see that the solid will increase in temperature because they are gaining kinetic energy and the particles are moving faster and faster and faster. Okay, it will reach a point over here, which is the first blue dotted line. It will reach a point such that the particles can no longer hold so much kinetic energy as a solid. Okay, the solid maximum has reached the maximum kinetic energy. At this point in time, you'll still continue to add heat, okay, but yes, it will be undergoing a change in state. So during this section, the solid will start to melt. Okay, and in the process of melting, it will take some time to melt. Your ice cube doesn't immediately within 1 second change to liquid. It will it will take a few seconds before it fully melts into a liquid. So during the process of melting, it will take some time. And in the process of melting, there is a mixture. Some of it will still be in a solid state. Some of it will be in a liquid. So you see an ice in a puddle of water. So there is two states, solids and liquids over here. And during this process, because the solid has already maximum kinetic energy, when you continue to add heat energy to it, the energy of the heat doesn't goes into the kinetic store. Instead, it goes into the potential store, the internal potential store of the particles. Remember, when we talk about internal energy of a substance, it consists of both kinetic and potential energy. So now the kinetic energy has reached a max. So all the energy will now go into the potential store. Okay, the potential energy. So potential energy is related to the forces of attraction. So I'm going to add in the energy in order to overcome the forces of attractions between the solid particles. So when I'm able to overcome some forces of attraction, then the solid particles are able to break free from one another and becomes a liquid where it is able to slide past each other and is slightly further apart. Okay, so during this process, the no energy goes into the kinetic store. That's why you know that kinetic energy is related to temperature. That's why the temperature doesn't change. The temperature remains constant. If it's a liquid or water, then the temperature will be 0 degrees. Okay, so during this process, temperature remains constant, kinetic energy remains constant, particles are gaining potential energy to overcome the forces of attraction. Okay, so once all the forces of attraction has been broken, it has changed a state to liquid. So over here at the second blue line over here, at this particular time, all the solid has melted to form a liquid. And then you know that in liquid, I will be able to hold more kinetic energy again because now my liquid, no, my particles doesn't only vibrate about their fixed position, they are able to slide past each other. So at this point in time, okay, if I continue to pump it in, then because all has already overcome the forces of attraction, all has become liquid particles, the liquid particles is now able to gain kinetic energy again. So the liquid particles will start to gain kinetic energy, then they will slide past each other faster and move slightly apart. Okay, but they still held together by strong forces of attraction. So at this section, kinetic energy increase, temperature increase. Again, up to this point where, oh, all my liquid particles have reached the maximum kinetic energy that it can hold. Then similarly, all the energy now transferred into the potential store to increase the potential energy of the particles in order to overcome the forces of attraction again. So now the liquid will start to break away from each other and become a gas. So during this section is boiling. There is a mixture of liquid and gas all the way until this section, whereby all the liquid particles have changed into gas, where they're able to take in more kinetic energy again, and the temperature will rise again as the gas particles gains kinetic energy. Okay, so this is basically how a heating curve looks like. Okay, so every time you see a flat line, it means that the temperature remains constant, the kinetic energy remains constant, and the particles are changing state. So the energy goes into the potential energy of the particles or the potential store of the particles. Okay, so and you also need to take note that during melting and boiling, there'll be a mixture of two different states, while at any other point where the temperature is increasing, is only a single state. Okay, so this one can be found in your textbook. So this one elaborates at 1, 3, and 5, where the temperature increase, you can read. Okay, energy is transferred to cause an increase in the kinetic energy and the particles to move faster. So the temperature increase because the kinetic energy increases. The potential energy, although over here they say the potential energy increases, but the increase is very minimal. Okay, so we can assume that the potential energy doesn't increase at 135. Okay, just let me jot down at 135. Okay, is the kinetic energy that is increasing. Okay, KE, KE. because the temperature increase, kinetic energy increase. Okay, and then at 2 and 4 is the one that the temperature doesn't change. It's a flat line. Okay, it means that it's changing state. So the first one will be melting, and then the second one will be boiling. So during this period of time, you should know that all the energy goes into doing work done against the attractive intermolecular force, or all the energy is used to overcome the intermolecular forces of attraction. So the separation becomes bigger, they change state, and the potential energy increases. So over here, okay, 2 and 4, the energy goes into the potential energy, the kinetic energy remains constant. Okay, so when one increase, the other one remains constant. Okay, so this is basically how a heating curve looks like and the explanation for it. Okay, I will not play the video. You can watch the video yourself at home. Now I go into a cooling curve. Cooling curve means I remove temperature, I remove heat from the substance. Okay, so if I were to remove heat from the substance, then the temperature will drop. Okay, so similarly, at 5, 3, 2, whenever you see there is a change in temperature, it means that the particles have loose kinetic energy. Okay, all the energy that comes out of the particles comes out from the kinetic store of the particles. The kinetic energy decreases and therefore the temperature decreases. Okay, let me just jot down over here. So 1, 3, and 5 is when it is losing kinetic energy. The particles are moving slower and slower and slower. Okay, 4 and 2 again is a flat line. It means that the temperature doesn't change. If the temperature doesn't change, kinetic energy is not changing. So what happens is the particles are at stage 4 and 2, the particles are actually losing energy because they are now not overcoming the forces of attraction. They are forming the forces of attraction to come closer together. They need to lose energy so that they can come closer together to form the forces of attraction between them. So at 2 and 4, I am actually losing potential energy. The potential energy decreases, but the kinetic energy remains constant. It's not moving slower, it's just moving closer together to form the forces of attraction. Okay, so this is a cooling curve. Okay, so summary, the internal energy of any substance is made out of kinetic energy of the particles, which is related to temperature, as well as potential energy of the particles, which is related to the forces of attraction or the distance. Okay, when heated, the internal energy will increase. It will go into either the kinetic store or the potential store. If the temperature increase, it's going into the kinetic store. If the temperature doesn't increase, means it's changing state, it goes into the potential store to overcome the forces of attraction. If it's cooled, the internal energy decreases. Either it loses as kinetic energy, the kinetic energy of the particles is decreasing. That means that the particles are moving slower and slower, or when the temperature remains constant, when it's changing state like freezing and condensation, the particles are coming closer and closer together to form the forces of attraction, to form stronger forces of attraction. So the potential energy decreases. Okay, next we move on into the next section, which is about boiling and evaporation. So over here, I have two pictures. One is evaporating. Okay, I just have a pail of water under the hot sunlight. You will see that eventually the entire pail of water will get evaporated, or a puddle of water on the road will dry up after a rainy day. Okay, so these are examples of evaporation, and I have another example of a beaker of water on a Bunsen burner, which is boiling. Okay, so just based on this picture that you can see, it's very obvious that there are some differences between evaporation and boiling. Number one, in evaporation, the water is very calm. You don't see much movement in the water. There is no air bubbles at all. There is no bubbles forming at all. You can't see bubbles forming in the evaporating process. But for boiling, how do I know that my water has boiled? Is when I start to see bubbles. Okay, so bubbles are usually present during boiling. So now we go into a table to show you the differences between evaporation and boiling. I'll go into the differences first, okay? So for boiling, usually we need a heat source. Okay, we need something to provide the heat. Okay, a strong heat because boiling takes place very fast. Okay, evaporation on the other hand, you don't really need a heat source. It gains energy from the surrounding. Okay, you don't really need to have a fire in order to have evaporation happening. Okay, but there's still some form of heat somewhere lah, but the heat is from the surrounding. Okay, and then boiling will take place throughout the entire liquid. So boiling and evaporation are both processes that involve a change of state from liquid to gaseous state. But for boiling, it takes place throughout the whole liquid. So even the liquid particles at the bottom of the beaker will also want to change into a gas. So that is what I mean by it takes place throughout the whole liquid. And because even the liquid at the bottom wants to change into a gas, it does change into a gas, and therefore it tries to escape out of the liquid as bubbles. So you see a lot of bubbles because the liquid at the bottom changes into a gas. So you see bubbles form. But evaporation, it doesn't happen to all the liquid molecules inside. It only happens at the liquid surface, at the top surface that is exposed to the environment, because only at the top surface where it's exposed to the environment, it is able to take in enough heat from the surrounding to break free, to overcome the forces of attraction, holding them as liquid particles and to change into gaseous state. So only the liquid particles at the top is able to change state to become a gas. So you don't see liquid particles at the bottom changing state. You don't see any bubbles. Okay, the one at the top just immediately go out to the surrounding as a gas. So no bubbles are formed. Boiling is a very fast process. Very fast, you have one whole beaker of water gone if you put under strong heat and it's boiling. But evaporation is a very slow process. It may take a long time because only water molecules at the top is escaping each time. There is not much energy being input into it. Okay, next one, boiling happens only at the boiling point. Okay, which is a fixed temperature for different substances. So for example, water boils at 100 degrees. Ethanol boils at 78 degrees. That means at 78, boiling will happen for ethanol. And at 100 degrees, boiling will happen for water. At any other temperature below 78 for ethanol, boiling will not take place. Below 100 for water, boiling will not take place. But evaporation happens all the time. Even before I reach my boiling point, I don't need to reach 100 degrees. I don't need to reach 78 for my ethanol. It happens even at room temperature. Okay, boiling will take place. Okay, and then during boiling process, the temperature remains constant. But during evaporation process, the temperature doesn't stay constant. In fact, evaporation will cause the objects to cool down. So it actually decreases the temperature of the surrounding during evaporation because it is absorbing heat energy from the surrounding. So in the process, it helps to cool down the surrounding and itself as well. Okay, so the similarities, both of them, is a change from liquid state to gaseous states. But you must be able to tell me the differences between them. Okay, then next I will zoom into how exactly does evaporation occurs. And in the process of evaporation, the one of the main function of evaporation is to cause cooling, a cooling effect. And how does the cooling effect comes about? And then we go and investigate what are some of the factors that affects the rate of evaporation. Okay, so this picture can be found in your textbook. This is exactly how evaporation takes place. So over here, you have a beaker of liquid, and this beaker of liquids, all the liquid particles are moving, constantly moving, okay, and they are moving, they slide past each other in random directions. Some of the molecules may have slightly more energy, some may have slightly less energy, okay, they move at slightly different speeds, okay, but usually during evaporation, evaporation occurs when the faster moving molecules at the surface of the liquid, so usually the one at the surface of the liquid usually have slightly more energy because it's able to absorb some energy from the surrounding. So it has a little bit more kinetic energy. So those particles with a little bit more kinetic energy, you can see is a longer arrow. Yes, a little bit more kinetic energy. It will move to the top, the surface of the liquid, and eventually they will have reached enough kinetic energy such that they are able to overcome the forces of attraction between them. So they have sufficient energy, they break free from the forces of attraction, and once they break free from the forces of attraction holding them together as a liquid, it becomes a gas. So it goes up into the air immediately. That's why evaporation only occurs at the surface. Okay, while particles that left behind, so all those with faster energy one will leave, okay, because they get energy from the surrounding, so they leave. And all those that leave are the faster ones, so they leave behind the liquids that are slower and slower moving. So the particles that left behind have slightly lower kinetic energy, okay, and with the average kinetic energy of the particles that is left behind is lower, decreases, as kinetic energy is related to temperature. So with lower kinetic energy, the temperature of the remaining liquids actually decreases. That's how evaporation causes cooling. So I repeat, faster moving molecules with higher kinetic energy are able to overcome the forces of attraction, holding them together, and escape into the air as gaseous molecules. This leave behind molecules with lower kinetic energy. So the average kinetic energy left behind is lower, and the temperature of the solution decreases. Okay, so that's how evaporation works. Evaporation causes cooling. So, when do you experience the cooling effect caused by evaporation? We have many uses. So, for example, human beings sweat whenever we are hot. What happens during sweating is that our body produces a lot of sweat because the sweat forms on the skin will take the heat away from the body, from the skin, to evaporate into the surrounding. So as your sweat evaporates, okay, it helps to cool down your body. It removes the heat from your skin in order to overcome the forces of attraction. And as it leaves behind the remaining sweat molecules with lower kinetic energy, and so the sweat becomes a little bit cooler on your body as well. So that's why you cool down as you sweat. It's how your body helps you to regulate your temperature. When you're too hot, you perspire, you sweat, and when the sweat evaporates, it helps to cool down your body. Okay, and then next also, you know that if you go for injection, they rub some alcohol wipes or alcohol swabs on your skin before injection. Number one is to kill the germs. Number two, as they wipe the alcohol swabs on your body, you will feel, oh, it's suddenly very cooling. Okay, it's cooling because alcohol is very volatile. It means it has a very low boiling point. Okay, so it evaporates very fast. So as you rub the alcohol on your body, it evaporates. As it evaporates, it takes away heat from your body again, and then it causes this cooling effect on the skin. The same happens like when you go for a swim. When you step out of the swimming pool, wow, you feel that suddenly I'm so cold when I step out of the swimming pool. Again, it's because once you step out of the swimming pool, water will start evaporating from your body. And this evaporation process causes cooling. That's why your body feels cold. Okay, so these are some examples of how evaporation causes cooling. Okay, then we go into what are some of the factors that may affect the rate of evaporation. So number one is pressure. Okay, so what happens? Pressure actually affects not only evaporation, it also affects boiling, which later on I'll share about how does pressure cooker works. So when the pressure is very high, pressure is caused by the gas molecules around it. So for example, let me draw a beaker. Okay, I have my liquids. Okay, if my gas pressure is very high, okay, my gas pressure is caused by all the gas molecules. Okay, if my pressure is very high, what happens is this pressure will push down on this liquid. So if I have water molecules that is trying to escape, I find it very hard to escape into the environment because of the high pressure pushing it down. The pressure will try to push down all the liquid molecules to prevent it from changing into a gaseous state. Okay, once it comes out, it tries to escape into the air. It kind of pushed down by the high pressure. So when the pressure is very high, the rate of evaporation is very low. Okay, it's harder for the molecules to evaporate. It's the same goes for boiling. When the pressure is very high, it's very hard for the liquid to escape. So it's also very hard for boiling to take place. That's why boiling, you will need more energy in order to boil because of the high pressure. So you reach a higher boiling point when the pressure is very high. But I'll talk about boiling point later on. Okay, next one, humidity of the air. Humidity is the amount of water vapor in the air. So if we say that, for example, Singapore has very high humidity because there's a lot of water vapors in the air. So you sweat a lot because all around you there's a lot of water vapor. But if you go to other countries, you realize that your skin will start to feel very dry because the humidity in other countries are lower and you don't sweat as much. Even though it's very hot, but you don't sweat as much because the humidity is lower. Okay, so the air is very dry. Humidity decreases in the aircon room also. So you switch on aircon room, you constantly stay in the aircon room. The humidity level is very low as well. Okay, so when the humidity level is low, is good because there's not a lot of water vapors at the surrounding. So a lot of water can come out to become water vapors. If the humidity is high, means there's a lot of water vapor already. Okay, I'm very concentrated in my air already, full of water vapor. It's harder for the water molecules to escape as water vapor because I'm already full of water vapor at the top. I don't want so much water vapor at the top. It's already concentrated. Okay, so when there's a high humidity, okay, the rate of evaporation is lower. Okay, so humidity of air, I skip over to wind over here. So that's why wind, when you have wind, your evaporation rate will be much faster because the wind will blow away all the water molecules. So you have water molecules escape, evaporate already, right? So you will form water vapor. If the water vapor all stay here, then you have very high humidity, then not much water molecules will want to come out anymore. So if you have wind, the wind will blow away all these water molecules. Okay, so it keeps the humidity level low. Okay, not a lot of water vapor here, so more water molecules can escape. The air will be drier, so more water can evaporate. So the evaporation rate will be higher when there's wind because it decreases the humidity level. Okay, next one, surface area. You know that you should know that if I have a larger exposed surface area, more molecules will be able to escape because molecules can only escape from the surface of the liquid. So if I have a very small surface, then only a small amount of water molecules can escape. But if I have a large surface area, more molecules will be at the surface, more molecules can escape. So you increase the rate of evaporation. Okay, and then obviously temperature, if you have a higher temperature surrounding, temperature is higher, the water molecules is able to absorb more heat, able to gain more kinetic energy, able to overcome the forces of attraction. So more liquid will evaporate. Okay, and then also boiling point. Usually liquids with very low boiling point like ethanol, the alcohol swap, very low boiling point, so it will evaporate much faster because it means that if I have a very low boiling point, means that I don't need to reach a very high temperature. I just need a small amount of energy. My molecules are able to overcome the forces of attraction. If I have very high boiling point, means that I need a lot of energy in order to overcome the forces of attraction to escape. So liquid with lower boiling point, we call it volatile liquids. They usually have very weak forces of attraction between them, very easily broken, so they have a higher rate of evaporation. Okay. Okay, then after that, we go into how does pressure causes a change in boiling point, which just now I mentioned as well. When you have a higher pressure, the pressure is pushing down the liquid. It's very hard for the liquid to escape uh, as a gas. So it's very hard for evaporation to occur. The same goes for boiling. So you can see this two person is on the mountaintop. So they are trying to cook a stew. Then the girl was saying, "Isn't the stew taking too long to cook? I'm getting very hungry." Yes, it's taking very long. I wish we have a pressure cooker. The stew will cook much faster. Okay, so they're camping at the top of a mountain. You should know that at the top of a mountain, the pressure is lower because there's lesser air molecules. So when the pressure is very low, okay, it is very easy. It will lower the boiling point because it's very easy for the liquid particles to escape up. So I only need a small amount of energy and then my liquid particles will be able to escape. So my boiling point becomes much lower. The temperature that I need in order to change state will become lower. So my boiling point is lower. And if the boiling point is lower, what happens is it's harder to cook food because your food will not reach that temperature. So for example, you want to cook stew. Okay, the stew needs to reach 100 degrees in order to be cooked. But now your temperature inside it has reached boiling point at 70 degrees. So already this pot hits 70 degrees, the temperature will remain constant at 70 degrees because it's already boiling. But 70 degrees is not enough to cook the beef or the meat. Okay, your meat will still be very raw, very uncooked. Okay, so this is what's happening. Then I go into what happens during a pressure cooker. I'm not going to play the video. You can watch the video. But I'm just going to explain the science behind the pressure cooker. So what happens in pressure cooker is, based on the word pressure, is going to increase the pressure. So you have a lid. Then you can adjust how much pressure is going to build up inside this. So as you heat the food, okay, some of the liquid or some of the vapor get vaporized. So you know that as you increase the temperature, okay, the particles are going to gain kinetic energy. Okay, some of it will evaporate to become a gaseous state. And then in the gaseous state, the particles will gain kinetic energy. Then they will collide with the walls of the container and with the surrounding particles more frequently and with larger force. Okay, more frequently, more violently. So it will exert larger force. And the gas pressure inside here, the entire pressure inside the pressure cooker will increase. Okay, as the pressure increases, what happens is it's going to push down on the food molecules or the liquid molecules inside the pressure cooker. As it pushes down, it's harder for the liquid particles to change state to gaseous. It's very hard for it to vaporize. And when it's very hard to vaporize, I continue to take in more energy. I reach a higher boiling point. I need more energy in order to vaporize. So as I reach a higher boiling point, I'm able to reach a higher boiling point. So for example, if you are just cooking water in a normal pan, exposed to the atmosphere, the water will just boil at 100 degrees. You put in a thermometer, it reads 100 degrees. But if you put the water in a pressure cooker, because of the high pressure pushing down, the vapor are all trapped inside, so that vapor cannot escape. The vapor is constantly pushing down on the liquid molecules. It will cause the liquid molecules to reach a temperature higher than 100 because I need more energy to escape. So it reached maybe a temperature of 120 or 130 degrees. So with a higher temperature, wow, your food will cook much faster. Instead of only reaching a maximum of 100, I can reach 130 easily in my pressure cooker. So the food will get cooked much faster. So that's how pressure cooker works. So summary, increased pressure above the hot water surface will make it more difficult for the steam to form, more difficult for the water to change into a steam, so more difficult for the steam to form and escape. So this will raise the boiling point of the water. With a higher boiling point, the food, or with a higher temperature, the food will be cooked much faster. Okay, so basically this is what happens in a pressure cooker. Okay, and then I will not show this video as well. This video shows you what happens when I lower the pressure. Okay, so how do I lower the pressure? This tube is connected to a vacuum pump, so it's going to suck out all the air molecules here. So when I have lesser air molecules, less frequent collision, less bombardment, less force per unit area, less pressure. So I have lesser pressure, much lesser pressure. Okay, I'm going to remove all the air particles here such that there's no pressure here. When there's no pressure here, you will realize that I don't even need to add a heat source. My water is boiling because when I have no pressure, the water is able to escape as a vapor, as a gas immediately. So it has a very low boiling point. So the water can even boil at room temperature. If I were to create a vacuum over here, low pressure, I reduce the pressure, I reduce the boiling point to even room temperature. So this is what it's trying to say. Okay, that's it for this part.